Hello, I'm Rui Wang. Here I'm presenting our work on ArkDB, a key value engine for scalable cloud storage services. This is a joint work with Zhu, Qingda, Shuo, Yikang, and Jason. On Alibaba Cloud, we provide multiple storage services. Three examples are OSS, Object Storage Service, NAS, File Storage Service, and Table Store, a NoSQL service. These services work on top of Pangu, an append-only distributed file system. They have an internal key value engine. For example, OSS uses the key value engine to store the mapping from object namespace to its layout and metadata. NAS uses the key value engine to store the mapping from file namespace to its layout and metadata. Table Store uses the key value engine to store user-created tables and system tables for schemas and ACLs. The key value engine itself sits on top of Pangu. This key value engine faces the following challenges. First, it sits on append-only distributed file system. Append-only storage demands garbage collection, which should be efficient. Moreover, SSDs are deployed widely in data centers for storage, and they should be utilized well. Second, range queries are issued frequently, and they need efficient support. Third, for some customers, ingestion workloads are dominant, and the background garbage collection should not impact the write throughput that much. For load balance, partitions may be split or merged on the fly. Such partition operations better be made lightweight. To scale out reads, read-only replicas are maintained. It is non-trivial to maintain read-only replicas on the same shared storage. Last, as always it is, faster recovery is needed for high availability. Our key value engine provides the basic capabilities of insert, delete, update, pointer lookup, and range scan. It supports transactions with snapshot isolation. Transaction logs and data are stored in append-only file streams. Each file stream consists of a sequence of extents. Extents are the truncation unit and the unit of sharing among file streams. Such sharing is called hard link. The old key value engine was based on an in-house developed LSM tree. We have developed a new one called ArkDB. ArkDB has a two-tier architecture. The memory tier uses whatever ordered in-memory data structure to support the desired data access semantics. The storage tier is indeed an on-storage BW tree. BW tree issues only sequential storage rights. In BW tree, a leaf page may consist of multiple data pages on storage. It maintains an in-memory mapping table to map a page ID to this page's most recent data page. So ArkDB combines the strengths of both LSM tree and BW tree. With a memory tier buffering, it supports high-rate ingestion. With on-storage BW tree, it performs range queries well, and the page-level compaction has less impact on user requests. Two-tier architecture is a starting point of ArkDB. It has more innovations include first, separation of system transaction log from user transaction log. It is better for restart recovery than classical B+ tree-based storage engine, which mixes user transaction log and system transaction log together. Second, separation of system transaction log from user data. This is better for both restart recovery and read-only replica redo recovery than classical BW tree, which mixes user data and system transaction log together. Third, separation of hard and cold data file streams. This helps reduce write amplification of garbage collection. Last, it utilizes file stream hard links to avoid storage duplication for partition split or merge. Partition split or merge involves cutting or stitching of B+ tree boundary pages, and they are very lightweight. This is the internal architecture of ArkDB. The memory tier contains memory buffers, page mapping table, and extended usage table. The storage tier consists of transaction logs, checkpoints, and data file streams. When a user transaction commits, its data changes are applied into memory buffers. When the memory buffer becomes full, it is flushed into data page stream. Flushing a memory buffer is called taking a user checkpoint. Upon page compaction, multiple data pages are merged into a base page. The base page is stored in base page stream. The page mapping table indeed contains the on-storage BW tree structure information. Both page compaction and the user checkpoint taking involve BW tree structural changes. These changes are wrapped in system transactions and recorded in system transaction log. When the system transaction commits, its changes are applied to page mapping table. Such changes result in extended usage changes. The extended usage table is updated accordingly. Both page mapping table and the extended usage table are dumped in the system checkpoints for recovery. The locations of the system checkpoints are recorded in metadata log. Next, we will drill down the core designs. Page mapping table contains the change history of on-storage BW tree structure. It maps the page ID to the page's on-storage location information. The page ID is physical and consists of extent ID and the offset in the extent. Page mapping table is shrinkable. Once our page's physical location information is updated into the parent page, this page ID's mapping information can be removed. The data page chains are two-dimensional. Each page mapping entry has a timestamp. Entry type can be base page, data page, or tombstone. Next pointer points along the first dimension. Origin pointer points along the second dimension. Each page rewrite entry indicates that our page is rewritten into multiple pages. Each new page has a high key. Let's look at the basic page mapping operations. In A, there are 3 data pages appended to PID1. They are PID 11, 12, and 13. These 3 pages are generated by system transactions with timestamp 100, 200, and 300 respectively. In B, when the data chain length reaches a threshold, and if they compared to the base page size, the total size of data pages has not reached a threshold, it will do a partial consolidation. That is, PID 11, 12, and 13 will merge into a new data page PID 14 without merging the base page PID 1. PID 14 points to the old chain on the second dimension. When a snapshot query comes to PID 14, if it tries to search as of 200, it will need to follow the second dimension. In case the total size of data pages reaches a threshold, all the data pages will be merged with the base page PID 1 and generate a new base page PID 15. In case after merging PID 11, 12, and 13 with base page PID 1, the resulting page is large and has to be rewritten into 2 pages, PID 16 and 17. A tombstone page is then generated with timestamp 400. This tombstone points to the old chain on the second dimension. Meanwhile, a page rewrite entry is generated to indicate this rewrite. Two system transactions can run concurrently and make somehow conflicting changes. Such changes are reconciliated. For example, we have this delta chain. One transaction does partial consolidation. The other transaction does append PID 18. These two types of changes are merged in the end. As another example, we have this same delta chain. One transaction merges PID 11, 12, and 13 with the base page PID 1, results in two pages PID 16 and 17. The other transaction does append PID 18. So we have a page rewrite as usual, but this new append PID 18 needs to be redistributed to PID 16 and 17 because PID 18 targeted at PID 1, which has been rewritten into two pages, PID 16 and 17. So PID 18 will be put into PID 16's delta chain, restricted with PID 16's key range. PID 18 will also be put into PID 17's delta chain, restricted with PID 17's key range. The following two examples demonstrate tree structural changes. PID 2 is an index page. It is rewritten into PID 21 and PID 22. Then PID 21 and PID 22 are posted into the parent page. So the parent page PID 3 is rewritten as PID 31 to include the new index terms PID 21, high key 21, and PID 22, high key 22. As another example, PID 4 and PID 5 are leaf pages. They have become empty, so they are deleted. Then the parent page PID 7 is rewritten as PID 71 to remove the index terms PID 4, high key 4, and PID 5, high key 5. PID 6 is a next index term in the parent. We need to create a page rewrite entry for both PID 4 and PID 5, which are conceptually related to PID 6. In this way, new delta pages targeting at PID 4 or PID 5 can be properly redistributed. On append-only storage, garbage collection is one of the most important components. We maintain extended usage table, which records the change history of extended usages. Each extend has an extended usage entry. The extended usage entry is shrinkable and spinable. It records as of snapshot system stamp, the valid size and the valid ranges. The usage change history after snapshot system stamp is recorded in usage log. The usage log is a list of incremental usage entries. Each incremental usage entry records the changes of size and ranges at system stamp. When the change history is merged into the snapshot, the data structure for valid ranges can be shrunk. For example, at timestamp 100, the valid range is 10 to 19. After adding two ranges and removing one range, the final valid range becomes 16 to 39. In case the count of valid ranges in a snapshot is too large, the whole valid ranges can be written into storage. The storage location is indicated by snapshot usage PID. Garbage collection occurs in rounds. Each round is a GC system transaction. It collects garbage for the extent with the largest garbage ratio as of GC snapshot timestamp. GC snapshot timestamp is bounded by mean read snapshot timestamp of all transactions. This is to ensure stability of extents for read. For an extent to become a GC candidate, its garbage ratio must be higher than a certain threshold. Since data pages tend to be short-lived, the threshold for data page stream extents is higher than that for base page stream extents. This helps reduce write amplification of GC. Queries for garbage ratio can be answered purely from in-memory tracked data. Query for valid ranges of an extent is needed only when this extent is garbage collected. Such a query may involve storage reads. Garbage collector relocates valid pages as of GC snapshot timestamp to the tail of delta page stream or base page stream, skipping garbage. After an extent is garbage collected, it can be truncated. Page relocation is a simpler form of page compaction without tree structural changes. Look at this example. It tries to relocate PID 11, assuming GC snapshot timestamp is 200. Partial consolidation can occur with PID 11 and 12 merged into delta page PID 14. Overwrite can occur with PID 11 and 12 merged with base page PID 1, becoming base page PID 15. This round of GC does not relocate PID 13. Here, I briefly mention more advanced features. In ArkDB, a snapshot is defined by user transaction timestamp and system transaction timestamp jointly. The two timestamps are correlated. With such two-level timestamping, there is no need to embed version numbers in records on storage in order to support snapshot isolation. ArkDB has efficient restart recovery due to separation of system transaction log from user transaction log. It also has efficient read-only replica continuous recovery due to separation of system transaction log from user data files. Moreover, it utilizes the hard link capability of the underlying file system to avoid the storage duplication during partition split or merge. Partition split or merge just needs to cut or stitch boundary pages of B+ trees, so it is very lightweight. We designed experiments to measure the performance of ArkDB. We verified the shrink capability of the page mapping table. We observed the benefit of separation of hot and cold data file streams. Compared to RocksDB, we verified the consistency of ingestion performance and the performance improvement on write-heavy and range query-intensive workloads. Finally, we measured the performance of ingestion and partition split on Pangu. Please look into the paper for more details. With that, questions?